Good. So the rest of the people is still recovering from support vector machines, I assume. Good. So we are entering the last phase of the Statistics for Data Science course. We are still in Bayesian inference, and today the topic is numerical methods for Bayesian inference, of course, and variational inference, which we will do after this section. In a way, are also numerical methods for Bayesian inference. They focus more on optimization, while these methods that we discussed today focus more on integration. But both topics, numerical methods here, which is more related to sampling-based stuff, although not exclusively, and variational inference are approaches to do Bayesian inference in the case where the model is a little bit more complex as compared to the conjugate model class. So remember that in the conjugate model class, we could compute the parameters of the posterior distribution by doing analytical derivations on the probabilistic model, so on the joint distribution of parameters and observable random variables. And this might not always be the case, and then the question is what to do then. So with what I'm presenting here, I'm following some stuff in Wassermann, some stuff in Held and Beauvais. These Monte Carlo methods or simulation-based methods are also popular in machine learning. There's a relatively old paper by Andrieux and others who discuss methods like the ones that we discuss here for Bayesian inference and machine learning, when Bayesian inference and machine learning was a little bit more popular maybe than it is today, although still today it's just always called variational inference, and in the 2000s it was more often called actually Bayesian inference than today. So I focus on in what we are doing here on the basic approaches. So first give some motivation why numerical methods are sometimes required, and then go kind of from simple to complex if you want, and leaving out what you might have seen sometimes, namely MCMC, which are specific sampling approaches based on Markov chain. So we are not going to discuss this. These are more complex sampling algorithms than the ones that we actually discussed, like point sampling and acceptance rejection sampling. If you want to understand MCMC, it's helpful to first understand what we are doing here, and then in the next step you can study MCMC. So that's kind of the plan. So you can see the whole thing a little bit in analogy to maximum likelihood estimation, where on the one hand we have maximum likelihood estimation like in the general linear model, or for parameters of the Gaussian if you want, where you can do maximum likelihood analytically. So that would be the same thing as doing Bayesian inference in the conjugate setting analytically, or you can do maximum likelihood estimation numerically, where you write down the log likelihood function and then you maximize it using some numerical maximization approach for nonlinear programming techniques, as discussed last Thursday on support vector machines, for example. And the numerical thing then in Bayesian inference would be something of the sort that we are looking at today, or variational inference. So let's start with motivation. So why care about numerical methods in Bayesian inference at all? So of course we have learned that the posterior distribution is central in Bayesian inference, and that for the for Bayes theorem to be evaluated, you need to evaluate the marginal probability of the data, which shows up as the denominator, right? The thing under the line. I recently have some problems again with confusing denominator, numerator, and Zähler and Nenner, but Nenner is denominator, I think. So where you have to evaluate the integral of the joint distribution over parameter space to get this. So in the, of course, and this is what you also see here, in the numerator, so above the fraction line, you have the prior and the likelihood, and these you define, yeah? So there is no, you don't need to compute anything, you just need to define a prior PDF or PMF and the likelihood, so often then in product terms, but there's nothing to compute. You just define them, and then you can of course also evaluate them by just plugging in, for example, data that you have observed. If you, however, want to make sure that your posterior distribution is normalized, that it means that it integrates to 1, you have to divide it by this normalization factor, and you should view this whole thing as a single number, because for given data you have x for 1 to n, so you have observed data, and then here you integrate over the parameters, so you have the PDF value for an observed data set, and that's just a number. Yeah? So it's just a normalization factor that you multiply the product of the prior and the likelihood with, so that this product of the prior and the likelihood integrates to 1. Again, the posterior is essentially the joint distribution, so the joint probability or joint PDF or joint PMF, but renormalized. Yeah? And if you want to do that, and the reason that you may want to do that is that you want to, for example, compute a Bayes estimator, and you need a real probability distribution. So if you, for example, just want to identify the map, then you don't necessarily need a probability distribution, but if you want to actually compute the posterior expected value, then you need a probability distribution, so you need to find this normalization factor. So as I said already, in conjugate models, you can do this whole thing analytically, and we will see in the Übung, we will do that for models of certain complexity. And as I said, also for the whole conjugate, for the exponential family, you can always do that. But modeling choices sometimes are such that these things then don't fall into that, and you still want to do Bayesian inference. So an example here is that you have a prior over theta being a normal distribution, and then the likelihood being Cauchy distributions, and then the posterior is proportional to this, and this is not analytically tractable. So if you don't believe that this is not analytically tractable, then integrate this. Yeah? Try to integrate it, and if you're successful, then let me know. But you will not be successful. Anyway, so this is just a basic example where where one can come up with not analytically tractable scenarios. And then again, even if the posterior distribution is analytically tractable, so if you can compute the posterior, here we have the posterior, then computing the expectation of some function under this distribution may again not be analytically possible. Again, you have to do an integral. This is somewhat the point here. Here you compute an integral to come up with a number, and here you compute an integral to come up with a number. And if you're lucky, this integral can be solved analytically. If not, then the question is what to do, and then the answer is, well, you can use methods for numerical integration. So the point here is that Bayesian inference in this setting has to do with the evaluation of integrals, and if these cannot be done analytically, if these cannot be evaluated analytically, then you can still often numerically integrate them. Yeah. So again, the point is Bayesian computation in this scenario corresponds to numerical integration, because one thing is the normalization factor for posterior inference, and then if you have the posterior, maybe from numerical integration, again you need to, if you want to have single numbers like Bayesian estimators that we discussed, then you need to integrate again. So numerical integration is then the topic. Yeah, and there are different ways to do numerical integration, so to approximate integrals. And the basic way to do that that you also learn in numerical mathematics, for example, is quadrature approaches, which is essentially a synonym for numerical integration in a deterministic fashion. Then one thing you always come across in machine learning books is the Laplace approximation to approximate integrals. And then there are sampling-based methods that are then referred to what is known as Monte Carlo integration. Monte Carlo methods is a little bit less specified. So Monte Carlo methods is anything where you use a random number generator, and Monte Carlo integration then is using random number generators to do numerical integration. And this is these are the methods that I basically want to introduce and give you some idea about. What we will also look at is for Monte Carlo integration, there are these more advanced sampling algorithms like importance sampling, acceptance rejection sampling, and Markov chain Monte Carlo sampling approaches. And we consider importance sampling and acceptance rejection sampling. What we will not do in the whole thing, there should be a new paragraph anyway. What we will not do is discuss the pros and cons of different methods. So don't ask me after the lecture, so what is the best of these? And what we also not consider is Markov chain-based sampling methods. So the pros and cons of different methods are of course interesting and important, but they of course require much more in-depth treatment, like error inequalities of these methods and computational complexity of these methods, then yeah, actually we have the time to be into, and also I have the time to prepare. So in general, I looked quite a lot at stuff that Art Owen from Stanford University, who has done a lot in Monte Carlo approaches, what he talks about, and he actually also advises basically to go along such a thing. So first look at what numerical integration can do, and then the story is always that numerical integration doesn't work that good for higher dimensional integration spaces, and then sampling, especially if there's some if the function that you're trying to integrate is zero most of the time, but only has some higher probability has some values non-zero in certain areas, then to use things like importance sampling. An MC-MC approach is kind of being the last resort if if nothing else helps. So that's kind of the story. Good. So that's the background motivation, and now we want to go over different ways to do numerical integration. But before, are there any questions based on this motivation and basic inference? No. Good. Then let's start with quadrature. So who of you has looked at quadrature in math? Oh, so in which course?
The numerics or computational mathematics.
Yeah. And so I'm basically only looking at the most basic thing here, actually Riemann sum, so I don't even go into trapezoidal rules. But what do you remember? So did you do Newton code formula?
Yeah, Newton codes, trapezoidal.
Yeah, so these are the typical things. So the idea is a little bit to approximate functions that you're trying to integrate with polynomials and then solve the integration for these polynomials analytically and then sum them up, right? That's roughly the idea. But I will only here give you the very basic idea from Riemann sums, which you should all know. And the main point is that I want to remind you that there are ways to do numerical integration. So if you have an integral that you cannot analytically integrate, you don't necessarily need to turn on some MCMC sampler. You can also just look at what has been around for numerical integration for a long time. So quadrature, it's often called quadrature, but essentially it's numerical integration. It's numerical mathematics. Story is that it works well for low-dimensional integration problems, and these are some examples. Like just briefly mentioned, you try to approximate the function that you're trying to integrate using polynomials. And I just want to briefly remind you of Riemann sums, just more with the aim of reminding you that there is something called numerical integration, and there are many methods, and they're very well understood, and you can learn about the errors. So if you do basic computation and you need to solve an integral, this is something you can turn to. So very basic, so Riemann sum and Riemann integral. So we're thinking here of a univariate revalued function, and we're thinking about an integral actually on a finite at a closed interval, sorry. And we assume that we have a partition of this interval into subintervals, where the first subinterval includes the lower bound of the integral, the last interval includes the upper bound, and then the Riemann sum is just the sum of the width of the subintervals, which is here called delta xi, which you get from subtracting xi minus 1 from xi, times a value xi star that falls into this subinterval, and this value x star you plug into the function f, and then you sum that all up. And the Riemann integral then is the limit of this Riemann sum for the width of these integrals, for the width of these intervals to go to 0. So nothing surprising here, very basic calculus. Only thing interesting here is that this x star I is only specified to be somewhere in this interval. For the Riemann integral, it does not matter where it is exactly, because you let this width of the integral go to 0. But of course, this already implies some way to approximate such integrals analytically, namely by evaluating the function that you want to integrate over a number of these x's that form this partition, and summing. No? So instead of doing an integration, you compute a finite sum. And that's a very basic form of numerical integration. So instead of solving the integral, you compute a sum. Now, with the Riemann approach, then come also like 3 rules for numerical integration, namely the left rule, the right rule, and the midpoint rule, and they relate to the question of how to choose this x star I. So if you choose this x star I to be the left point of each subinterval, then it's called the left rule. If you choose the right or upper boundary of these subintervals, that's called the right rule. And then the thing that then starts to get interesting for numerical integration is the midpoint rule, where you actually use the midpoint of this interval, which then if you go into more details about this, which we will also see on the next slide, already corresponds to approximating this function f by a first order polynomial, so by a straight line in these subintervals. This we've already seen. Yeah, often equipartitions are assumed, and what you are doing here is that you essentially approximate f by piecewise constant functions, as we see here. So, so this is straight from Wikipedia. Here for the left rule, so of course the idea is that you approximate this integral, so the area under the curve for the left, and you do this by summing up the values of these areas. For the left rule you have these areas. For the right rule you have these areas, so here you would overestimate the integral, you would underestimate the integral, and for the midpoint you choose these values, so you have the this area, which maybe from these three options looks the best, and you can also show that this corresponds to assuming a straight line between the endpoints and integrating over that. Yeah. So what this is not difficult or exciting or anything. I'm just trying to remind you that that you don't need to sample necessarily. You don't need to do Monte Carlo integration. You don't need to do MC if you want to numerically evaluate an integral. Yeah. So that was the point here. Questions about this? No. And there's a whole field in numerical mathematics on numerical integration. So if you open a book on numerical analysis or numerical mathematics, there's a chapter discussing the relationships, the errors, and the ideas of many of these integration rules. So start there. And of course, they are also implemented in software packages. Good. Then as a second way to approximate integrals in an analytical way, so by not necessarily turning on a computer. Of course, if you want to evaluate such quadrature formulas, in the end you of course will do this also using a computer, but in principle you could write down the sum and sum it up yourself. So you don't need a computer and you don't need to generate random numbers, and that's the main point here. So in terms of it's kind of a deterministic approximation. The second thing to discuss then is the Laplace approximation, something that you always find in machine learning books for some reason. Who has studied Laplace approximation? No one. And it's not the Laplace approximation that Carl Friston talks about in variational base. That's just to confuse everyone. So that's the Laplace approximation from machine learning that we are discussing now. Yeah. So open Bishop, Barber, any machine learning book that deals with Bayesian computation, you find the Laplace approximation. So it's this. So Laplace approximation, like all the stuff that we discuss here, is a method to solve integrals, and here I'm in a way reintroducing this again with its relation to Bayesian inference. So for example, if you want to approximate a posterior expectation of this form, where you have the posterior distribution, you have some function of the parameter, like we had earlier, for example, the identity function, so the expected value, and you want to evaluate this, but you don't have the functional form of the posterior distribution. So of course, Laplace approximation you can use for any kind of these integrals, but here kind of one point is that you can use it in Bayesian inference. Although you don't know the posterior distribution, the functional form, you can evaluate, for example, a Bayesian estimator, like the minimum mean squared Bayesian estimator, meaning the posterior expectation. Yeah, so that's nice, because if you want to give a Bayes estimator, you don't need to evaluate the posterior distribution. You save quite a lot. Of course, then you don't have the posterior distribution, but at least you have a Bayes estimator. And the Laplace approximation, so the Laplace approximation, as it's always used in machine learning and Bayesian statistics, refers to doing this, and it's based on what is called Laplace integral approximation method. So that's a method to approximate integrals I guess due to Laplace, although these things are of course always not due to the person that they're named after, but somebody else, usually before. So to understand how that works, so how you can evaluate the posterior expected value of the parameter without knowing the posterior distribution, we are first going to look at what Laplace integral approximation is. Yeah? Good. What is Laplace integral approximation? That's the following. Assume you have a univariate real-valued convex and twice differential function f with a minimum at x tilde. Yeah. Then a reasonable approximation of the integral in from minus infinity to infinity of the exponential of minus n fx is given by the exponential of minus n f evaluated at the location of the minimum times the square root of 2 pi divided by n kappa, where kappa is the second derivative of the function f evaluated at the minimum, and because x tilde is a minimum, this kappa is larger than 0. Yeah? So if you, what this means is, if you want to evaluate such an integral here, an integral of this form, then you don't have to, here you have a function of course, then you not necessarily have to compute the antiderivative and then solve this indefinite integral. And that's the question again, are these called indefinite integrals or the other way? The one thing is where you have this antiderivative function, and the other thing is where you have the boundaries to be infinity. I think we had this before, where I wasn't quite sure whether these are called indefinite integrals or the other ones. Anyway, but so if you want to compute this integral, or at least approximate it, then instead of computing the antiderivative and then solving things, you can also evaluate the minimum and the value of the second derivative at location of the minimum, and then evaluate this formula. So where you only plug the minimum into the function and multiply by 2 pi divided by n kappa, and it's roughly that. That's of course surprising. So why does it hold? It holds due to a second Taylor approximation of f. So this is why this whole thing becomes approximate, because instead of really evaluating this integral for f, you evaluate this integral for a second order Taylor approximation of f. And what is used is that the integral of this, I think it's also called the Gaussian integral, evaluates to the square root of pi divided by a. So this is of course something that you see all the time when you talk about the normal distribution, because you normalize this term by the inverse of this term, so 1 divided by square root of 2 pi sigma square. We will not prove that this is the case, we just assume that this is known. There are proofs doing this, for example, with polar coordinates and so on. So we just basically want to see why this holds in a second. And what I'm saying here, a reasonable approximation of the integral is that the approximation error decreases as n gets large. Yeah. So of course everything approximates everything, so you can also approximate any integral by 2. It's also an approximation. The question is it a good approximation when for every integral that you ever encounter you take 2? And it's usually not reasonable, so an approximation is always the question, does it get better somehow? And here one can show, and we will also do that, that the approximation error decreases for n going to infinity. So the question is then, why does Laplace integral approximation method work? And this is this motivation here. It's not really a proof, I feel. It's more motivation. So because we're not showing that the error decreases or something like this, we just motivate this approximation. So consider a second order Taylor approximation of f in its minimum. then of course at the location of the minimum the first derivative is 0, and we can define kappa as this thing here, this f2 prime, so the second derivative at the location of the minimum. And then, well, if we use this suggested, so if we look at this integral and plug this in, then we first get this, and then we can take we solve the brackets, and then we can write these as 2 exponentials, and then we can one of the exponentials is fixed with respect to the integration constant, so we can take it out. And then we have here this Gaussian integral, which, as we've seen previously or know, evaluates to this, and then we have already rewritten this integral like this. So this is very straightforward, and one sees that it's based on the tail approximation. Yeah, so this is Laplace integral approximation method. So to approximate an integral of this form with this value. Now this was not the Laplace approximation yet, this was just Laplace integral approximation method. Now the Laplace approximation. Now comes the Laplace approximation. So assume we have this probabilistic model, and it's like always, one thing that is important for the whole thing to work is that the data points are conditionally independent given the parameters. So this joint distribution of the data points factorizes into the factor terms of each individual data point probability given the parameter. And we want to evaluate this posterior expectation of f. So maybe I've done that on previous slides already. So you often see these also written as conditional expectations, which is also makes sense, so that you see the expectation and then you see f theta given x1 to n. Conditional expectations are not that straightforward because one has to read them as random variables and so on. So I'm trying to emphasize here always just that with this subscript that we want to compute the integral of f theta times p theta given x1 to n with respect to theta. So that's this notation here. Now, if we want to compute this, then a reasonable approximation of this is this formula here. You take the square root of kappa 1 and kappa 2, which we have to discuss what they are, times the exponential of minus n h2 theta tilde 2 minus h1 theta tilde 1. So you might already see a little bit that this looks a lot like this. So of course this is where this is coming from. Now the question is, what are these functions h1 and h2? They are defined here. So it's a log of the function that you're interested in, the log of each individual likelihood and the prior, and h2 doesn't involve the function f theta. And what is also required are the minimum points of these functions h1 and h2, and the kappa 1 and kappa 2 are the second derivatives of these functions h1 and h2 evaluated at these minimum points. Now the point, or the main point here, is that it's about the expectation with respect to the posterior, but as you can see here in this approximation and everything that is here, the posterior doesn't come in, right? So here you have the likelihood and the prior, likelihood, prior, and here you have the function f, but you don't need the functional form of the posterior distribution. This is kind of the neat thing about this. So you can evaluate a posterior expectation without actually computing the posterior. The reasonable here again means that the error decreases. Of course, you need to evaluate the second derivatives of these function h's, and you need to find the minima of these function h1 and h2. And this can either be done hopefully analytically. We will discuss one of an example from the help book in the Übung. If this is not analytically available, then of course you can find a minimum using a numerical optimization, and then you would have translated this integration problem to an optimization problem. Yeah? Good. So that's kind of how that works. So if you want to evaluate this posterior expectation, do this. And then the question is, why does this work? And this is then what I here wrote up as the motivation for the Laplace approximation. And of course, it works essentially because the definitions are as the definitions are, and using Laplace integral approximation method. So what I'm first doing here is to, this is a typo. This should be x1 to n. Actually, I replaced all of the x's that were in there yesterday with x1 to n, but I missed obviously one. So the first thing that is done is that this posterior expectation is rewritten in terms of these integral terms. There we are actually also missing a d theta. Why do I only see the typos when I'm presenting them? But at least then I see them. And yeah, this is basic reformulation, so we don't have to go over it step by step. And so it's basically writing out the joint distribution and the marginal. And then we have this, and we're also missing the d theta. Then we have this ratio, and then we can approximate each of these integrals using a Laplace integration approximation method, which was explained previously, and then we get the formula that was proposed here. Yeah. So again, just rewriting the posterior expectation. Using the definition then of these functions h1 and h2, and then using twice Laplace integral approximation method yields this. Yeah, so fairly straightforward, and that's Laplace approximation. Now, questions about this? No, that's the famous Laplace approximation. Okay, yeah, I think we can do basic of Monte Carlo integration before the break because it's really quick. So what is now Monte Carlo integration? So what we've seen so far is, or maybe we do it after the break and I just talk a little bit so that the break is not too long. What we've seen so far are kind of deterministic integration approaches. So this one was an approximation where we have a formula to approximate the integral, which doesn't require the posterior distribution, but there is no sampling involved. So we don't need to turn on a random number generator. We might turn on a numerical minimization algorithm, which might have stochastic starting points, and then we in a way turn on a random number generator, but we don't need to. And also the Quadrature approaches, they don't require turning on a random number generator. So the remaining things now require turning on a random number generator, and the first thing to discuss there is Monte Carlo integration. Now we've covered another minute and we can have a break. Good, then for a basic approach to do numerical integration by turning on a random number generator, and then two sampling algorithms, so random number generator algorithms that often are used in this context. That was the basic thing about Monte Carlo integration. So, as I now said multiple times, Monte Carlo integration is a means to approximate integrals using random sampling. Oh, sorry. And the question is why this whole thing is called Monte Carlo, which is also a little bit annoying that it's called Monte Carlo. Allegedly, this has to do with a Manhattan project where they started sampling approaches for integral evaluations and Metropolis Hastings algorithm, MCMC, and apparently, or allegedly, better, they refer to sampling there as Monte Carlo. Whatever. So I find it a little bit annoying that it's called Monte Carlo, because for a long time I always try to figure out what is the difference between Monte Carlo and random sampling, and there is none. So why call it Monte Carlo? It seems, and this is the basic story about these errors and so and the approximation errors with respect to numerical integration, that in high dimensional integrations spaces, Monte Carlo integration works better, especially if the function that you're trying to integrate is non-zero over a specific part of the integration space. But that said, when I prepared for this, yeah, it's not that easy. You also, specifically if you do Monte Carlo integration, you also have to care about the variance of the Monte Carlo, so the variability depending on the random samples, and this not necessarily gets better. So it's a complex story that we're also not going to get into regarding the pros and cons of different methods. And essentially, the idea is that instead of partitioning now, like in a Riemann sum, the space over which you want to integrate in a deterministic manner, you sample points, and then you evaluate the sample points using the function, and then you average. So that's the basic idea. So that's the Monte Carlo here estimator and Monte Carlo algorithm. So again, we assume that we want to evaluate an integral, which we consider an expected value of a function f under some probability distribution. So here it's x. Of course, this can be, if we talk about Bayesian inference, this can be, of course, always be a posterior parameter distribution. So if this little x here is the parameter, so this is just written up in general for random variable x, where x, of course, could also be a parameter. And we assume that we want to evaluate such an integral, and we assume that we can sample n points from, or n realizations from identical and independent copies of x. So again, this just means that we assume that there are n independent identically distributed random variables. And then we already know, of course, for a long time that we can estimate such an expectation. So, for example, if f is the identity function, by the sample mean. Yeah? So this is really just using the sample mean to approximate, to estimate an expectation. The only thing that we make more general here is that we assume that that there's a function that is not necessarily the identity function, but the basic point is we approximate an integral by a sample mean, or if you say it differently, an expected value by the sample mean. And this estimator, so where we estimate values and then sum them all up and divide by the number of n, is called the Monte Carlo estimator of this integral. Yeah? So it's not really something new, it's just saying something that we previously discussed more in the context of, okay, we have parameters that we want to estimate, or we have features of random variables that we want to estimate, like an expected value. We estimate this by a sample mean. We are now focusing, or this focus is more on the fact that actually the expected value is an integral, so we can use the sample mean to estimate integral values. A Monte Carlo algorithm then, of course, is also very fairly straightforward. So you first sample these random variables according to the distribution of interest, and then you evaluate the sample mean. Fairly straightforward. Now, because, and actually we already know this, so the sample mean is an unbiased and consistent estimator of the expected value. So the Monte Carlo estimator is also unbiased and consistent, and it, in an unbiased and consistent way, estimates the integral of interest. So this is the same proof as we've seen before. I think the difference is that there's now this additional function f, but with respect to the unbiasedness, we're interested in the expectation of the Monte Carlo estimator, and then we can put the expectation operation based on the linearity of integrals further in, and then we see that the expectation of the Monte Carlo estimator is the same thing as the expectation of the function f of x, which is the unbiasedness, and then the consistency, without going much into that, is of course, as we discussed earlier when we discussed frequency statistics, consistency is essentially equivalent to the laws of large numbers, that say if the number of random variables gets larger and larger, then the probability that the sample mean deviates by some value epsilon from the expected value, this probability goes to 0 for whatever small epsilon you choose. And this is the same thing as the consistency of the estimator. So that's the very basic story about Monte Carlo integration. So sample mean to estimate expected value, and in the back of your head you should have that expected value is an integral, so estimate the integral. Of course, there's not only the biasness and the consistency, but there's also the variance of these estimators. And what this means is, if you now, for example, run such a Monte Carlo estimate, that if you run it again, you will get something slightly different out. And if you run it again, you will also get something slightly different out. And of course, the question is how variable this is. And this is, of course, also studied in detail. So one can talk about the variance of Monte Carlo estimators. Then there are methods to minimize this variance. And these methods, they depend on the sampling scheme. And this is the whole Monte Carlo estimator variance reduction story, which I also don't go into details here. But that's of course something to keep in mind. And this is also something that always, in a way, made me a little bit reluctant to use Monte Carlo approaches in my own work, in my own scientific work, because if you use these sampling approaches, then of course the analysis that you do is not fully reproducible, so there is not a deterministic mapping from the data you acquire to the results that you have, but there's a stochastic mapping from the data you acquire to the results that you have, because if you would redo the analysis, something slightly different comes out. And of course then the method is to do the analysis many times and average, but again, then you have an average. And so you have these two kinds of random contributions. First of all, your data is somehow randomly generated, and then your analysis that comes out is also induces further randomness. So this is what kept me philosophically more rather than pragmatically away from doing Monte Carlo stuff myself. I'm not saying that Monte Carlo is bad or anything, but one needs to keep this in mind, that if one uses this Monte Carlo estimator, that each time one runs the analysis, something slightly different will come out. Of course, this slightly different will be really small. And if you talk about instead of doing numerical optimization and you have rounding errors and so on, then also in numerical optimization, slightly different things will come out. So it's not that clear cut if you go into the details, but philosophically, that's what kept me not using Monte Carlo much myself. Another thing is that, of course, the reason why I went more into variational inference is because that's also the idea, or some people propose that this is how the brain works, so doing Bayesian inference, and then I somehow like it more to think that the brain does something deterministically and doesn't sample. But of course you can argue if you want that there are so many neurons and maybe you have physics stochastic noise and then there's some sampling going on in the brain and averaging. But yeah, that's a whole different story. Anyway, Monte Carlo estimator, for example, if you want to evaluate this integral, what you would do is you want to evaluate this over 0 and 1, and a simple thing that you can do is now sample n values from a uniform distribution over 0 and 1, plug them into the integrand, so the thing that you want to integrate, and compute the average. And then you have a Monte Carlo estimate. And of course, in a way, this is a little bit simpler than coding up, for example, a numerical integration rule. So this is maybe why I sometimes see people using Monte Carlo estimation of integrals fairly quickly, because it's I don't know how intuitive this is, but it's definitely simple to do, and you don't have to think much.
In this example, I think I didn't get to link the integral to a definition of the Monte Carlo estimator, where we say we have the expectation of a function of x. So this example would be PDF. So my PDF, I don't know if it's univariate, but I don't see it.
No, yeah, that's a good point. You don't see the px, right?
Yeah.
That's a good point. So this is, I should have written it in. Here this would be the uniform distribution over 0 and 1, which you then, because that's just 1, and it's constant over x, you can just take out and not write it in here.
Yeah.
So, but it's a good point to make this explicit. So there's px, which is 1 in there. Yeah.
Okay.
In some way, the point also was here to show that this choice over uniform, if you have this definite integral over some interval, for which you can always write down the value of the uniform outside of the integral, then you're only dealing with integrals, and you don't even, so it's feels more like integral evaluation, even more than doing expected values. Good. So this is the very basic idea of Monte Carlo integration. And then when you look into the books on Bayesian computation, what they fairly quickly then go into is now specialized sampling algorithms. And then the motivation for these specialized sampling algorithms is that you may or may not want to use them for Monte Carlo integration. Yeah, so one has to keep that a little bit separate. So importance sampling and acceptance rejection sampling are methods to generate random numbers based on certain constraints. So importance sampling essentially using random numbers from one distribution to have to evaluate an expected value under some other distribution, and acceptance rejection sampling using one distribution to actually create samples from another distribution. The question is, why is this of interest in Bayesian inference, and so where's the relation? And the relation is then that you can use importance sampling or acceptance rejection sampling for Monte Carlo integration, for example, to compute the normalization constant for Bayesian inference in scenarios where you cannot simply sample from the distribution of interest. So that's the reasoning. Yeah. So these importance sampling, acceptance, rejection sampling, being kind of specific methods in the context of Monte Carlo integration. So first, importance sampling. Now, importance sampling again is a method to approximate expected values of this form, like Monte Carlo integration itself. But now the idea is that you may have a random number generator to sample x according to some distribution q instead of a distribution p. Of course, this is all, I mean, if you now have all these toolboxes where you have many random number generators, then this sometimes feels a little bit obsolete. On the other hand, if I compare the number of random number generators that are implemented in MATLAB compared to what I see in NumPy and SciPy, maybe I should rather compare to R, but in NumPy and SciPy, definitely the selection of random number generators in Python at this point in time feels definitely smaller than it is in MATLAB at this point in time. And like 10 years ago, also in MATLAB, there were fewer random number generators. And this is also why we, for example, in the beginning discussed this probability integral transform, where essentially you only need a uniform random number generator, and then you can generate random numbers from all parametric distributions that you're interested in. And of course, in the old days, when we only had this uniform random number generator, where the professor had to go each morning and collect the random numbers from the Brunnen, then this was more relevant. If you now, for something that you want to sample, have the random number generator, then of course you don't need to do this. Although, having said that, again, importance sampling can also be beneficial in scenarios where you actually want to sample only in a certain area of the integral space, so there are other uses. And it can also be applied if you don't know the normalization constants, which is helpful in Bayesian inference. So there's a little bit of a bigger story. So this is what I said earlier, they can be used to reduce the variance of Monte Carlo estimators. However, this story is a little bit too big for the lecture, so I'm just telling you what importance sampling really is and its various uses in computation you can then study for yourself. So what is importance sampling, irrespective of its use? Importance sampling rests on what I call here the importance sampling identity. So if you have two probability density functions q and p, and you have a space x, which is a subset of the real numbers, and on this space qx is larger than 0 for all x that have also p being larger than 0, then the expected value of f of x under px can be written as the expected value of fx times wx under qx. So the main thing is here that instead of evaluating the expected value under px, you evaluate a different expected value under qx, and they are the same. And the different expected value is given by weighting this function f according to this ratio. And why this holds is relatively really straightforward. So the expected value of fx is this integral. Now you can multiply and divide by qx. Then you can define this weighting function, and then you have here fx times wx times qx, and this is of course just the expected value of this. So yeah, this just basically shows why one expected value can be written, so one expected value under one probability density function can be written as the expected value under a different probability density. And P and Q in this setting of importance sampling are referred to as the nominal and the importance distribution. So P is what you actually want to do, and Q is how you sample. I won't say this correctly, we will see it on the next slide. Yeah, so P is nominal, so this is what you actually, where you actually want to evaluate the integral or the expected value, while Q is what you actually sample from. So let P and Q be probability density functions like before, and now assume you want to evaluate this integral, and assume that you have a random number generator that generates values from Q. Then you can estimate this integral, which is this expected value under P, based on the Monte Carlo estimator essentially that you generate using Q. And what you need to do is you need to evaluate the function xi and multiply it with this weighting function wxi. So this again shows that this is unbiased. So if you evaluate the expected value of this estimator here under Qx, and of course you need to plug that in, get the Qx into that, and then we've already seen previously on the previous slide that this is the same, and hence you have an unbiased estimator, and then of course lazy, as I'm known to be, consistency follows with the law of large numbers. Yeah. So this is basically just showing that if you want to evaluate an expected value under P and you have a random number generator for Q, if you can evaluate, of course, what you always need to do is put your values xi through P and Q. So you need to know these functional forms. But if you know this, can compute this, and everything is well defined, so that you don't need to divide, or you don't divide by 0, then you can use this. And it's also, and this is why this W is introduced here, you can see this as a prototypical thing of a more general approach where you weight these values f according to some criteria to achieve something. Now this thing, yeah, we don't have to go in that much detail, but this is normalized importance sampling, and here the point is that you don't need to know the normalization constants for neither P or Q, because essentially the they cancel out. So it's shown on the next slide. So this is, for example, helpful if you want to compute a posterior expected value, but you don't know the posterior distribution or you only know the posterior distribution up to the normalization constant, because you only know the prior and the likelihood, and you don't want to solve or evaluate the normalization factor. And then you can actually use normalized importance sampling without knowing the posterior, again, to evaluate a posterior expectation, like for the Laplace approximation. So essentially it's very much as in the previous case, only that we now assume that we have these unnormalized versions. So this so P tilde is the unnormalized distribution P, which gets normalized by this constant. This is the unnormalized version Q, which gets normalized by this constant. Of course, if you know the normalization constant, you can just set P tilde to be Q directly and C to be 1. And why this holds is then shown on the next slide. So again, it's slightly different, of course, from what we've seen before, because here it's now the expectation under Qx of this, but then divided by the expectation of Qx of this weight function. And yeah, in a way you can already based on this get the idea that, for example, that the normalization constants just cancel out. So the first question is, why does this hold? So, which I call the normalized importance sampling identity, as compared with this identity here, which is the importance sampling identity. Well, yeah, plugging things in. So putting things in, you get to this, and then putting in the normalization constants without changing anything everywhere, and then cancelling a little bit out, writing the normalized ones in, then writing out the integrals, getting the qx in, and cancelling certain things out, and wulle cancelling out, and then you end up here. So it's really straightforward. You just rewrite the integral based on the definition, and based on this, then you can also do Monte Carlo integration by evaluating this normalized importance sampler of mu, which is a typo, it needs to be of I. So the point here, so this normalized importance sampling, this is kind of, if you are happy with importance sampling, then normalized importance sampling I mainly put in here because it feels a little bit closer to the aim of Bayesian inference, where you, for example, don't have the posterior distribution, and hence you avoid evaluating the normalization constant first. But the logic of doing this is just the same, and you're just lucky that the normalization constants actually cancel out in this approach. Yeah, so that was importance sampling. So yeah, so it's a way to do Monte Carlo estimation of integrals.
Can you give, I mean, it's I understood you have a P distribution, you assume it's through this, and then you take a Q, I guess, where it's easier to sample it for a number. Can you just give an example, maybe just to picture in which situation I would?
Yeah, so it's in the situation that Python has so far only implemented a Gaussian random number generator and a uniform random number generator, but you now have analytically, for example, come up with a better Bernoulli model, and you now want to evaluate the expected. Now, better is a stupid example because you know the analytical solution for an integral, but no, not necessarily. Let's assume you want to integrate 1 over 1 plus x squared under a better distribution, which you feel a little bit lazy to really start now going analytically to it. And you also don't have a random number generator for the better distribution. And in this case, you can use this if you have your uniform random number generator. And you could also use a probability integral transform. But this is kind of the scenario. I think this, so that's the basic motivation. If one, I think, but there I really don't know that much about. If you, or better, you don't know anything about. If you use this for minimizing the variance of a Monte Carlo estimator, because, for example, if you do Monte Carlo estimation based on a certain distribution, you know that, and as compared to importance sampling, that you know that the variance is smaller, then this is also a motivation. So that that you want to do Monte Carlo integration, you have your random number generator, but you already know that the variance would be smaller if you use importance sampling. Then use importance sampling.
So in this case, you assume the xi's you're sampling. You assume that it's difficult to better because of your.
Now, in this case, I wouldn't say so. If you use it for variance minimization, then it's not necessarily more difficult, but you have a guarantee that the importance sampling estimator has smaller variance than the basic Monte Carlo estimator. So that would be the scenario. Good. Yeah, it's actually a good question about the motivation, because if you these numerical ways are also, or these numerical approaches, I haven't used personally at all, or maybe only once or so for something that I don't remember. Mainly I'm doing a variational inference if it comes to basic computation or conjugate inference. But also when I read the books, it's always like importance sampling, acceptance, rejection, but then they explain how the algorithm works, but it's usually the motivation doesn't get quite clear. That's I also tried to search or tried hard to find a motivation, because if you have, yeah, it's interesting, but why would I use this? And this I find is not necessarily explained best in the books that I'm reading. So it feels like one has to cover things like importance sampling, acceptance, and MCMC. But why we would use that, it's not necessarily completely clear. But I included whatever I found as motivation here, obviously. Good. Acceptance rejection sampling. That's now a method to obtain samples. This is even more basic than importance sampling, which was about approximating intervals. This is only about creating random numbers. And it's a method to obtain samples from some variable y, which is distributed according to a distribution py, by sampling another distribution. And this is, of course, very similar to the probability integral transform method that we discussed fairly early on. Because there you basically can create random numbers from any distribution based on the uniform distribution, and this is basically working. So I think the main motivation to discuss acceptance rejection sampling is actually its relationship to MC-MC methods, which we will not discuss, and I also don't know much about. But so to motivate this now, if you know that you have the probability integral transform, or especially if you know that you have all the random number generators that you ever need in your package, is a little bit hard to motivate. Of course, don't forget that the random number generators that are implemented in these packages, they of course rely on these kind of things. I mean, they don't do crazy stuff, so they usually then use a uniform random number generator and modify it. Yeah, that's what I said. And the idea is you strategically reject samples from X. So you induce a sampling bias in samples from X. So you basically, if you think you're sampling from a Gaussian, then you accept certain samples from the Gaussian and others you reject. And then your censored sample has a new distribution that is not a Gaussian, and the distribution of which follows from how you reject it in a strategic way, how you rejected samples. Yeah, and if for some reason sampling from the posterior, so this is me trying to motivate that in the current setting, if sampling from the posterior distribution is difficult and you don't want to use importance sampling, then you can use acceptance rejection sampling to get random numbers from the posterior, which you then can use for Monte Carlo integration. So what is acceptance rejection sampling? So how does it work? So you start with two probability density functions, one called the proposal density and the other one the target density. And the assumption is that you can obtain random samples from the distribution of X. The assumption is also that you can evaluate the function corresponding to the ratio of the probability density function of Y and the probability density function of X, and that Py is smaller or equal to Px for all values defined on a constant. And there we can actually make pictures, which I didn't include. If all of this holds, then you can use an acceptance rejection algorithm, which works as follows. So you draw from the proposal density, then you draw another random variable u from the uniform distribution, and decide whether to keep this sample of x for a sample of y if your u is smaller than the ratio of p y of x divided by cp x of x. If you basically do this, so you sample first an x and evaluate this, and then you sample an u, and then you decide whether you keep this x and call it now a sample of y, or else you take a new sample from the proposal density. Then you're doing acceptance rejection sampling. And the magic then of this is that by keeping the y's in this manner, the samples of x, but then calling them y, these y's will be distributed according to this probability density. So that's the magic. And the magic, of course, can be shown to hold based on proof. Yeah, and this proof is not that straightforward, because you have these two random numbers, and one needs to clarify what one actually does there. So you have the joint distribution of x, which is distributed according to px, and of u, which is distributed according to a uniform distribution, and you condition the distribution of x on the fact that the random variable u is smaller than this ratio here. And this is what I tried to, based on some stuff that I found in the literature, try to develop here. So the question is about this conditional probability. So I'm setting up a joint distribution over both of them, and then look at the whole thing, of course, here always from this CDF way, so looking at events where things are smaller or equal to x and u is smaller or equal to some value fx, and then by rewriting things, actually I don't remember exactly the details here, we come up with that the CDF, so the probability for x to be smaller than a value x, given that u is smaller than this value f of x, corresponds to the CDF of y. So so have a look at this if you want to understand how this works or why that works. The bottom line, and what's in a way the first thing that you should remember, is that you have these two random variables, and you strategically, based on this other random variable, reject things. But it's actually not that trivial. So because I mean it would be less complex if you sample and then you just have a cut off something, right? So you reject if this value is larger than 10, and you accept if this value is smaller than 10. This, of course, wouldn't yield any sensible, but it would be simple. But here you the decision to reject or not to reject, you base on the outcome of another random variable. And that's what makes this then interesting.
I don't really get it at all. What you're doing, I mean, in the first step, do you adjust the px for the distribution? Or
no. So this is one task in the Übung, is to implement this. So one exercise. No, you don't adjust anything. You just you need to find this constant such that py is smaller or equal to px for all values of x and y, which is always assumed to have the same outcome space. So because you take the samples of x to then be called samples of y, so if you have a univariate x, your y can only be univariate. You need to find this constant, and then what you do is you take a sample of x, you evaluate py for this sample, px for this sample, compute this ratio, and then you ask whether so you have, this is a number then, yeah, the number, but the number depends on this sample. Yeah, so this here is a number. So for example, if you sample 3, this comes out, for example, to 2.5. If you sample 4, no, sorry, it must be, because, sorry, that didn't make sense. This is a number between 0 and 1, so that it makes sense with respect to the uniform distribution. Because py is smaller than this, this is always smaller than 1, and it's larger than 0 because it's these are probability density functions, and c is not 0. And so here you always get a number between 0 and 1. So again, you sample, for example, 3, so you get 0.7. And then you sample 2, then here you get, I don't know, 0.4. Then, if you, for a given sample, you have this number, you sample a uniform random variable, and check whether the outcome of this realization is smaller than this thing that you just have computed based on the sample. And if it is, then you accept the sample x, and if it is not, then you didn't get a sample for your y, and get a new one here. And it's surprising that this works.
Yeah, I understand the algorithm, and I think I get it what we're doing, but I don't get why it should work.
Yeah, and that I agree. I also don't. So when first sees this algorithm, it's very surprising that this works. And why it works, well, that's this proof. So we can no, we cannot, because time is up. Yeah, but this is so go through the proof. Actually, this function f(x), that's maybe a little bit confusing here. This function f(x) is just this ratio. But what it shows, what the proof shows, is that the conditional distribution of x given the event that this uniform random number is smaller than this ratio, so than this. So this conditional probability evaluates to the CDF, or of course this is a CDF. So this CDF of x, conditional on u being smaller than this ratio, evaluates to the CDF of y. And it's surprising. Yeah. But I think the proof works, but one has to start with the joint distribution of the events that x is smaller than small x and u is smaller than this constant. Good. So this was our little trip into numerical methods. So once, and this is also why the reason why I went into acceptance rejection, because originally I wanted to present MCMC, and then I read MCMC and I didn't understand why this works, and then I figured that I only understand why MCMC works once I have understood why acceptance rejection works, and then yeah, I figured that there's you cannot just introduce MC because it's completely unclear why this should work. And so my suggestion is, if you want to understand MC, first clarify for yourself everything that we did today, and then it's you have the basic motivation and basic foundations to understand why MC works. We will, however, not now continue in these sampling approaches and go to MC because everything that we've seen here you can also do. You don't have to do MC. We will go to variation effects next, where we don't use random number generators, but we again maximize and optimize. Good, then see you in a bit in the exercise. Übung.